So, have you ever wondered how an insurance company seems to predict the future? Or how scientists can tell if a new drug is actually working? Well, it all kicks off with a surprisingly simple mathematical idea. Today, we're diving into a question that honestly affects everything from your life insurance policy to major public health studies. How do you mathematically model that huge uncertainty? The transition from being alive to, well, not. How do you put a number on mortality itself? The answer, it turns out, lies in this really elegant and powerful tool that actuaries and statisticians use. It's called the two-state Markov model. And the real magic of this model is its simplicity. I mean, it ignores all the messy, complex details of a person's life and just boils everything down to a single fundamental transition. The way it frames the problem is by defining just two possible states for any individual. You're either alive or you're dead. That's it. It sounds pretty stark, right? But it's that very simplification that allows us to get a useful answer from a super complex reality. And if you were to draw it, it's literally just this, a one-way street. You can move from the alive state to the dead state, but yeah, there's no arrow going back. It's a single, irreversible jump. Now, to make this model actually predictive, we need one crucial number. It's often called the transition intensity, shown by the Greek letter mu, but you can just think of it as the force of mortality or even just the death rate. It's the instantaneous risk that someone who's alive right now will transition to the dead state. This little number is the engine that drives the whole model. Okay, so like any powerful tool, this model has a few important rules or assumptions that we need to get our heads around to see how it works. The whole thing really rests on three core assumptions. Now, the second and third ones are important for the math, for sure, but it's that first one, the Markov assumption, that has the most powerful and kind of counterintuitive idea. And this is the big one. The Markov assumption says the model is basically memoryless. It doesn't care if you've run a marathon every day or if you have a risky job. All that matters is your current state. You are alive. It's kind of like a board game. Your next move only depends on the square you're on right now, not all the squares you've landed on before. It's a massive simplification, but it's what makes the model work. Okay, so we've got the model and we've got its rules, but how do we actually find that all-important number, mu, from real-world data? This is the central question for anyone using this model, isn't it? It all comes down to finding the best possible estimate for that death rate. And after all that theory, the answer is beautifully, almost shockingly simple. The best estimate for the death rate is just the total number of deaths you observed divided by the total amount of time you observed everyone. Deaths per unit of time. That's it. The source material we're looking at puts it perfectly. It's just so reassuring when a really complex mathematical approach leads you to a result that is fundamentally intuitive. The math confirms what our common sense was telling us all along. Let's make this totally concrete with an example. So imagine a scientist on the savannah, and they're studying a huge group of newborn wildebeest. So the key here isn't just counting the animals. The scientist has to calculate the total time all 1,282 of them were alive. Some live the full year, others don't. So you add up every single individual lifetime, and that gives you the denominator, what statisticians call the total time the group was exposed to risk. Then the formula is easy. Total deaths divided by total time exposed to risk. Now, that's one way to model this problem, by tracking every single lifetime. But it turns out there's another, often simpler way to get to the same answer, especially when you're dealing with really big populations. It's called the Poisson model, and instead of tracking each individual's time to death, it just counts the total number of deaths over a period. It treats them as rare, random events, kind of like counting the number of emails that hit your inbox in any given minute. And this is where it gets really beautiful statistically. You have two different paths, the exact Markov model, which tracks individuals, and the approximate Poisson model, which just counts events. And yet, they both lead to the exact same intuitive formula for estimating the death rate. It's amazing. The Poisson model is perfect for questions just like this. Imagine a big company with 5,000 workers. For planning purposes, they need to know the probability of a certain number of deaths occurring in their workforce over the next 6 months. So first, they'd use the death rate to figure out the average number of deaths they should expect. In this case, it's 2. From there, the Poisson formula can calculate the specific probability of seeing 0 deaths, 1 death, or 2 deaths. You just add those probabilities together and boom, you find the chance of seeing fewer than 3 deaths total is about 68%. Okay, so let's zoom out. We've gone through the theory, the assumptions, and the formulas. But why is this simple idea of modeling just two states so absolutely fundamental?
It all comes down to this one core concept: exposed to risk. That's the technical term for that total observation time we calculated for the wild beast. And getting that denominator right, accurately measuring the total time a group is exposed to any kind of hazard, is a cornerstone of modern statistics.
And this concept of events per unit of exposure is everywhere once you start looking for it. It's how life insurance is priced. It's how we know if a new drug works better than a placebo. It's how car insurance rates are set. It's how epidemiologists track the course of a disease. It all comes back to this one powerful idea. In the end, the true power of this model isn't in what it includes, but in what it bravely leaves out. It proves that sometimes the best way to understand a complex system isn't to add more detail, but to find the courage to simplify. So the question to leave you with is this: what other complex problems could we solve if only we could find the simple model hiding at their core?